In the 1800s, it was discovered that if you shone light onto a metal surface, electrons would be emitted. And this is not surprising. Light is, after all, energy. And so the idea is that the electrons absorb the energy, and when they have enough, they're able to leave the surface. And the more energy they can absorb, so in other words, the more intense the light, then you would expect the electrons to have more kinetic energy. They would be able to absorb more, and consequently, they'll have more as they leave, a higher kinetic energy. But this is not what happened. In fact, what happened is that only if the light was above a certain frequency would electrons be emitted. And below that frequency, which is known as the cutoff frequency, it didn't matter how intense the light was. It didn't matter how intense it was, no electrons would be emitted. And above that frequency, the intensity of the light only affected the number of electrons emitted, not how much kinetic energy those electrons had. So this was a baffling result for physicists. It became known as the photoelectric effect, and Einstein is the one who ultimately explained what's going on, and he won the Nobel Prize for his efforts. The idea is that light is not just a wave, it's also a particle. That particle is known as the photon, and that means that the energy that is involved in the light actually comes in what we refer to as discrete packets. There are specific amounts that it comes in. What are those amounts? Well, it turns out the formula is E equals hf. So this is the energy of a photon. This is the frequency, and h is known as Planck's constant. It has a value of 6.626 times 10 to the negative 34th joule seconds. And what Einstein showed is that the max kinetic energy that an electron will have is equal to the photon energy minus what is known as the work function. The work function is how much energy is needed for the electron to break free. And you can see that if the frequency is too small, you're going to get a negative number here. And we know kinetic energy can't be negative. So this explains why below the cutoff frequency, you're not going to get any electrons ejected because they won't have enough kinetic energy. Okay, it would get a negative value, which is impossible. And speaking of the cutoff frequency, to find that cutoff frequency, you let the kinetic energy equal 0, and then you have h times f naught being the cutoff frequency. Okay? And then here we can solve for the cutoff frequency pretty easily. I could solve for that or the work function, whatever you want. So we normally would just write it like this. Now, the other thing that this explained, this whole idea explained, is why if you increase the intensity, that only affects the number of electrons ejected, not their individual kinetic energies. Because once they're ejected, they're not absorbing photons anymore. They're ejected, okay? They've already absorbed a photon, the individual electron, it's absorbed a photon, and so that's going to dictate how much kinetic energy it has. Now, making the light more intense means more photons, so that means more electrons will be emitted. So this idea put forth by Einstein, which was built upon the work of others, explained the photoelectric effect. And this effect is important, not just because I'm making you do some problems on it, but this essentially is what's going on with solar panels, with solar cells. This is how we get solar energy. The light comes in and the electrons are absorbing energy, or absorbing those photons. And that's allowing them to move, and we're getting a current from that. Now, I want to be clear, we're not building solar cells based on the photoelectric effect, at least not that I'm aware of. There's actually more involved process, but this basic idea of the energy coming in discrete packets is important for solar cells. And it's actually one of the issues with solar cells. You want to get that cutoff frequency essentially down low so you're able to absorb more energy from the sun and thus produce more electricity. One other thing to mention here with regards to the photoelectric effect is the stopping potential. So we can talk about the max kinetic energy being equal to E times V naught, where V naught, this is how much voltage we have to apply down here to this metal surface to keep electrons from being ejected. Okay? And this here, this E, is the charge magnitude on an electron. And so this is one way that you can experimentally determine what Ke max is by just applying this voltage. But this also gives rise to a unit known as the electron volt. Okay? So if you let E be 1 and you let V be 1, that would be 1 electron volt. Okay? So if I let E be 1 and V naught is 1, then I get 1 electron volt. And 1 electron volt, this is how we write it, 1 eV, is equal to 1.6 times 10 to the negative 19th joules. And on top of that, we can talk about H, if we're using electron volts, 4.14125 times 10 to the negative 15th electron volt seconds. We often use electron volts because when we're talking about individual particles, the energies involved are so small. And so the electron volt is just a much easier, a much more convenient unit to use as opposed to using joules. But again, this is 1 electron volt. It's defined as the amount of energy that a single electron will have if it's accelerated through a potential of 1 volt. That's all.